and share the slides.
It's gonna be me, and there is 3 slides. One a contribution from Moritz, which I will also cover since he was his conflicts. And I will start, for those who follow the slides on the web page, with the contribution which is called workshop R&D. Okay, so this is the first one I will start, but you can certainly also see it in the screen in a second when I share this. Here we go, share screen. Pop. That should be visible.
Yep, go ahead.
Perfect. So this is a contribution to show another part which we would like to sustain with ACTS, which is yes, a toolkit for deployment in experiments, but also a platform where you can do R&D in a rather simplified way. And coming back to my roadmap, this is basically the bottom right corner. That's pretty much inspired also by the tracking machine learning challenge, not so much or not entirely by the challenge itself, but by the fact that the data set around has been used and reused in several different projects. And I'll come to the hopefully soon to be finished spin-off of this at the end. So that's just a flash of a few old slides actually of the TrackML dataset that has been used in several different projects. HepTRKX is now has now been followed up by ExaTRKX, but there's quantum annealing approaches, whatever. A lot of the people actually used this data set, and there's examples of seed classifications. For instance, this is an example where you try to do a neural network classification of seeds. Are they good or not? If they are good, follow them and invest the time into track following. If they're not good, don't invest the time, basically, as a crux of it. So that was an example, also based on the same data set and simulator on quadruplet seeds, which you feed into a neural network with different architectures. You can play around there, and then you try to classify this, and that in this very optimistic scenario can give you a really good seed classification. I said there's an optimistic scenario, and I don't want to go into the details of this work, but rather to show what we would like to support, what sort of research. The second is the next contribution I will give you after this this talk is the slides Moritz prepared on the data format itself, N-born example, which is the probably our most progressed pipeline based on hashing and similarity learning. And then there is research on graph networks, or this is a Siamese network, neural network for vertexing. Also interesting stuff, and I will link the talk from Bastian at connecting the dots in. The idea there is you build a big adjacency matrix, and then you identify the blocks in the matrix, and that basically are your vertexing blocks. There's of course R&D you need to do, dissolve off diagonal elements whatsoever. Coming back, I don't want to go into details what's all done. That's not ACTS work per se, but that's having a test bed for R&D of that sort is something which we always had in our project description. Now, although all of those examples, and there's many more, if you go to the Connecting the Dots conference, you see way more of those, are using the data set and the test bed itself. We have not yet done a full backporting of such an approach into the core code or even the examples core, meaning a full pipeline of, let's take an ML external library, put it in, feed it with something, and spark it or enhance the standard reconstruction with it. At the moment, most of this R&D is done in ML frameworks, as it's obviously also designed for, but we sort of need to understand if this is a fruitful R&D project, how to bring that back into the code. I think no one is going to argue for running an ML framework per se as a reconstruction framework. So coming back, this is closes this cycle. Practically, this red line is something I also would like to discuss at this workshop, is if what experience people have to use ML libraries they used they did for the research, to bring them back into some production code. So let's skip out here, and I will stop sharing for a second. If there's a question right now on this, we can actually stop here for a moment, Heather.
Okay, I don't see any in the live notes, but if anyone has one, feel free to speak up.
Okay, then I will go to the contribution, which is called Talk ACTS Workshop Algorithms. And this is the slides that Moritz prepared. And I'll go back to share, hopefully, in a second. And you get the full screen again. And here we are. So what tools are there within or in the ecosystem of ACTS for algorithm R&D? There's a common data format. There are already common data sets, not yet to the extent as we want to have. And then how to use this and how to already bind this with an experiment. There's an example of the hashing and metric learning pipeline. So don't probably have to go into this very much, but the typical historical HEP data is very nested data in strategy and also in code. So you have relationships from hits to parameter to tracks, the parameters to it, etc. You probably know that well enough that we don't have to go into detail. That, however, when we did the TrackML challenge data set, turned out to be conceptually way too complicated to make it work with either people from outside the field or with even libraries. So the template we came up with for the machine learning data set is the flattest event data format you can imagine. It's really block event data format as of comma separated values with different files and index linking between that. So I think for those having worked in the very past with common block and Fortran, they probably are reminded to data structures that have been in use. What is the TrackML format is practically a particle 4-vector information, including the time. Then it does the simulation and energy loss and scattering, and then creates truth hits. And for this, also due to the effect that it was used for the TrackML challenges, there is Python readers and writers, such that you can even load events into your Jupyter notebook, and that's a lot where this is from. So on top of the TrackML detector, we have worked on a detector called the Open Data Detector, which is available since quite a long time in the ACTS examples. There is a to-do. I put a few more slides in afterwards, which we can go very quickly through. Bottom line there is, it's very close to be validated, and Moritz is leading this activity together with Stani. to see that we have at least the tracker or the tracking part of the open data detector validated. Now I'll show you one example what we did with this data, and this is the hashing approach of track reconstruction. So practically finding an optimal hash function that groups the hits together into a unique number, and would then be a track number that would be ideal to have. That's a function, however, does not exist, but approximate versions of this can exist, and this is the idea of this R&D, mainly conducted by Sabrina and co, where you basically try to find a data structure, a hashing data structure, which pre-groups you the hits. And in this example, it's done with a bucketing strategy. So you practically try to find projections of the space, and this is with a random projections done that pre-groups the hits in something which is called approximate nearest neighborhood. And the good thing is there is a lot of extremely well tested and highly optimized libraries out there, mainly by big tech players. The two that have been tried mostly were the one from Spotify that basically looks for close by songs in the Spotify library, or the navigable small world from Facebook, which is just also looking for similarity data in the massive Facebook data set. So the idea there is basically you take your complicated hits and via bucketing produce data structures in which you could even do local track reconstruction or clustering, which is the most time-consuming part, but you reduced it into such a small area that it is actually almost instant in execution time. So that's how well these libraries work. This is, I think, the Annoy library showing how often are trackable tracks in a bucket. So how many buckets do you need to query to have all trackable tracks found? And you can see this with different sizes, with requirement of different sizes. The idea there is basically you take this hashing library, pre-bucket the data, and then run local reconstruction starting from this, which is sort of an automated seeding approach. You can improve this with metric learning, so you practically try to learn a multi-dimensional feature metric that represents your data a little better. This is an illustration here on the side. This, however, is the real TrackML data set, a view of it where you can see an XY view of hits somewhere in the detector, pre and past metric learning. So you can pretty much understand that any sort of clustering in the learned space would probably outperform the spatial one. Something that feeds into the next item is, can we run something like this on accelerators? This was one of the reasons why we tried actually the Facebook library, because they have a dedicated GPU backend that produces almost identical results in the bucketing. You can see here on the left side CPU and GPU compared. And you benefit, of course, from the speed up. So you see the number of bucket queries at the bottom, and you see the time in millisecond at the left. So it's really pretty fast to pre-bucket the data and then have enough buckets thrown that you're almost that you almost certainly have hit each trackable particle at least once. So this we implemented, and there is this is probably the most interesting part also for the workshop, because this we have run already also with the Atlas ITK data, so simulated data, not only with TrackML. However, we had to come up with a rather complicated pipeline that talks between Atlas reconstruction, even with intermediate files, to do that. And one of the ideas, and this was my last slide of the talk before, is if we would like to support something like bucketing driven reconstruction, what does it technically involve, rather than running jobs with intermediate files? How can we put that together into one running pipeline? It actually works. These 2 tracks are brought to you by Spotify, if I'm not mistaken. So this is a bucket with the reconstruction running inside, and that's then of course a very, very small problem to do track reconstruction in there. And the following is basically just the completion of the results that have been shown at the Connecting the Dots conference. So this is one example. I think what we should try to discuss out of is how can we put such a pipeline back into production code that runs as part of a HEP framework. That would be an interesting thing to discuss on Thursday from my point of view. And then I leave it for here. I think in the interest of time, how are we doing? The last contribution on this this item is the status of the Open Data Detector, which is a GEANT4ified version of the TrackML detector, pretty detailedly modeled, also pretty detailed in terms of material, not probably as heavy as one would actually build such a thing, but good enough, non-symmetric, and is currently under validation. There are also some validation plots. That's for your further information afterwards.
Great. Thanks, Andy. Any questions? People are being quite quiet in the live notes so far. Maybe I'll start with one. So you talked about you had to do, well, sorry, can you share the slides again? It's actually on your slide.
Sure, absolutely.
So you were saying you had to do kind of a complicated interaction to get this running between Atlas software and ACTS. Can you say a little bit more about that and how it might be fixed for the future?
Yeah, let me just see I'll share like this. That should be okay.
Yeah, that's fine.
Yeah? Okay.
It just might be easiest to see the picture. That's why I suggested sharing again.
So the main problem of this is one of the problems we had here is that, of course, neither a Facebook library or the Spotify library are per se accessible from an algorithm stack in Athena, right? So you sort of you sort of need either to update the externals in a way that you can access this, or you make a breakpoint, write out the data, then run it somewhere in a different framework and feedback. And since we had to do this basically in a way that the bucketing was an intermediate step of this pipeline, there was the hit writing, then the bucketing, and then the list of buckets was with hit identifiers was fed back to Athena, and then the local reconstruction with track following would run within the buckets. So that is quite complicated, as I said. What you would of course like to have is, can an experiment framework like Gaudi, or we could start with our test framework, do that in an optimal way within the event execution. Basically, have a bucketing module running and local reconstruction inside the buckets.
Okay, so it's mostly a problem in the externals, and so this would be something I would have to resolve if you wanted to use it for reconstruction in general. Makes sense. Other questions?
Excuse me, can you hear me?
Yes, please go ahead.
on slide 12 or 13, I forgot. I wonder the dependence of the bucket on the tracking detector. For example, we have pixel in 2 dimensions and strips, and even I don't know whether the implementation of the bucket is an easy issue, or we just need a very abstract and very common.
So yeah,
please.
So the input for this bucketing method was really XYZ coordinates, and then enhanced with some features if you have cluster information, etc., etc. But this is one of the ideas of this project, is also to see how transferable such an approach is from one detector setup to another detector setup. And so far it has been tried on the TrackML detector and the ITK, Atlas ITK. That turned out to be rather easy to just refill the data structure, since it's just a metric. It auto adapts to the data, and that's one of that would be one of the great benefits, of course, of such a setup, that you don't have to tune, that it would basically adapt to the special information of your data.
Thank you.
Okay, any other questions? Okay, I don't see any, so thanks, Andy. Let's move on, and I'm just going to stop and start the recording while Georgiana gets set up with her slides.